by looking at and knowing something about the rate of change of something happening, whether it's oil being spilled or rocket-powered basketballs rising into the air, or we'll talk next, but I think it's sand being poured onto a scale, something like that. So, but if we can measure at what rate something's happening, our goal is to be able to figure out what happened because of that rate. So if there was one rate all the time, that's a pretty easy question. Like the driving 50 miles an hour for however long you want, it's really easy to describe how far you've driven after any number of given hours has elapsed. Or even if it was something like minutes or seconds, you could just quick unit conversions and answer it pretty easily. It's when you have rates of change that vary. In this case, we were talking about most recently as time goes on, as time elapses from the time that the rocket basketball was launched. We had that rising at first near zero rate, and then it increased to be rising faster and faster. So if I wanted to describe its height, well, its height's going from height, we said, suppose it starts at 0 and then increases. Well, the height increases more and more quickly, so how do I figure out what its height is other than that general description, rises more and more quickly, which is just describing the rate in reality. So if I talk about something like this, so suppose this red curvy thing here, which the formula for that, just by the way, is that, ooh, where did it go? Which isn't really important here, but it's kind of crazy looking, and it won't stay for whatever reason. But something with sine functions and squareds and everything else. So in any case, if this is a rate of change of something, so y's per x, whatever the units are, I can see for most of this I've got positive rates. We've got negative rates past 18 and 3/4 or so. But I can see positive rates, so something, whatever it is increasing at varying rates, increasing slowly and then more quickly, and then more slowly, and then more quickly, and kind of cyclical, but always increasing up until between 18 and 20 someplace, at which point whatever this is starts decreasing, or we start de-accumulating something, whether it's losing money, losing altitude, whatever it might be. But our process, in order to use these varying rates, since we don't have any like magic to use, just math, if we use the techniques of constant rate of change to give ourselves estimates for what happens, then we can later, after we set up the process for how we're going to form these estimates, we can make those estimates better and better just by changing the value of a parameter. And the parameter that we were using was, well, let me freeze this when it's not all the way over there. So if you can see what's going on here, we've got, as this goes across, we've got these horizontal lines that are being formed, and you've drawn some of those. What those were, that's horizontal line instead of a curve. So instead of a rate of change that was changing all the time, we had it stay constant for small intervals at a time. How long are those intervals? Well, it's the distance between these red dots here, or the distance that's indicated by the single purple question mark there, and I forget which of these is which. But I've got a lot of questions, I don't remember which is what. But if I imagine one constant rate from here to there, now this one doesn't start at 0. And in lots of cases, if you're doing your own, making up your own equation, you can say, well, whatever this process is I'm measuring, let's say it starts at time 0, or I'm going to start at time 0. But you don't have to for any reason. It's just sometimes that's convenient. Like if somebody had already had some sort of equation where we had time measured in years since 2000 as the independent variable, but you had something that's only started occurring in 2012, you can say, all right, I'm just going to start measuring something that happens after 2012. So I'm going to start at 2012, t equals 12, instead of starting at 0, because that doesn't make any sense. And rather than making all new numbers and saying 2012 is year 0, like, just, all right, let's start at 12 and go on from there. We can start from wherever. We'll use the symbol lowercase a to indicate where we're going to start our accumulation from in a generic sense. If it's a realistic problem, there would be a number, some value of the independent variable at which we start measuring accumulation, or that we care about measuring accumulation from. And then we form our intervals after that. So starting at A, we're going to go forward by chunks at a time. Each of these small chunks, we're going to call that a delta x in general with interval. I think we had delta t earlier. I'm going to undo all these mystery question marks. I don't remember which one is what, so I'll just pull them all up. And we'll talk about the meaning of the rest of these. I think that's about all of them. Yep, that's all of them. So in this picture here then, I can see that as x increases, I can measure change within the interval that x happens to be in, like how much I've used this most recent rate. And there's also change from all the previous rates. If you remember talking about trying to write out that piecewise accumulation function, we're going to avoid doing that by just trying to explain in general how many pieces we've already got full intervals for versus what's happened in the most recent piece, the piece where x currently is. So we can talk about the complete or completed intervals and the current interval, the one where wherever as x increases, the one that it's in at the time. Because the reason we want to separate those is for calculating rate of change. If I want to know what happened or amount of change, if I know how fast something's happening at a constant rate times how long it happened for, or the interval for which I allow that rate to remain constant, the product of those two, that mdx, gives me my dy, the change in accumulation. So again, I'm going to freeze this at some larger value. So this first interval here, I was using this low rate that looks to be a little bit above 0.5. And if x is this big, something larger than that, way past that first interval, then I don't have to worry about where x is within this interval and how long I use that rate for. I know how long. I'm using it for, well, the determined width of my intervals. These look like a little bit more than 1 in this picture, but I'll just call it delta x. So delta x we'll use in general, or delta t, for the width, a fixed width, that just our parameter that we're choosing for how often we're going to sample our exact rate function. And then also that means how long I'm going to use one constant rate at a time for. So I use this first rate for delta x, the second rate for delta x, the third rate for delta x, the fourth rate for delta x, and so on until I get to the interval that our x is in the middle of, in which case I'm going to use this last rate here for only, well, dx, the typical value we use for what's our small variation in x. It's just how far it's gone into this interval, and I don't know what it is, but whatever the x value is minus wherever the beginning of the interval is, that's how long I've used it for. So our goal is going to be to generalize this process of finding what happened due to the rate by doing rate times time, rate times time, rate times time, or mdx, mdx, mdx with a bunch of different m's over small complete intervals, plus one stray interval at the end that your x can be in the middle of, maybe, like if it's a specific numerical value, but how in general to describe the extra part that's due to the current interval added onto all of that, so I can have a total accumulation starting from a onward. So there's net accumulation since time a, since value a, whatever x or the independent variable might be representative of. There's a couple other things I wanted to point out on here besides that a, our r sub f again, that with the subscript, that would be the exact rate of change function notation. Without the subscript, that indicates it's an estimate. So if you don't see a picture, if you just see the notation, r sub f versus r, the difference is rate of change exact for function f, and then r is just representative of an approximate rate of change function formed this way, using constant rates for small intervals, delta x. There's this left of x here. So left is a function that it's not an official, like everyone knows this math function. There's other ways to define this. We're going to define this, but basically I want to refer to the point at the beginning of each interval as I pass it, so that when x is small, x left of x is the x value at the beginning of the interval that it's at, which would be the same as a. When I pop into the next interval, left of x is the beginning of that second interval. When I pop into the third interval, left of x is the x value at the beginning of that interval. So left of x is something we'll define in a minute, more like half an hour or so, that tells me the value at the left end, the x value at the left end of the interval that x is currently in. And why that's useful is because the left ends of intervals is where I evaluate my exact rate function and use that rate for a while. So I'm going to evaluate my exact rate function at only places that are left of x at some point in time. So when x is down here, left of x is this. So left of x is only one value at a time, but it takes on all these indicated red dot values as x increases in this diagram. So left of x is kind of like a tell me where the beginning of this interval was function. So it rounds down the x value in that sense. All right, so let's get back to the rocket basketball instead of this general view. But our overall goal, again, is to measure accumulation due to a rate that was actually varying all the time, but we'll pretend that it's constant for delta x or delta t units at a time. So we left off thinking about this. So we have an actual function rule this time. So if you want to write out by substituting in values to this function, you could. If you want to use function notation, you can. But let's start at time 0 and think about intervals of width 0.9 seconds long. We've got a velocity function that's measured in meters per second, v of t or r sub h of t, call it either one. This is from your book, and in your book I believe it's called v of t, but I'll just use the r notation for exact rate of change of function h for height. So r sub h of t is t to the 1.3 power. Here's a picture of it. And we want to estimate this at several different points if my goal were, as this task 1 says, to try to estimate the accumulation. So in other words, estimate the height achieved during the first 5 seconds. And I know we talked about on Tuesday, since we have intervals of 0.9, 9/10 of a second, I'm going to go through 5 full intervals plus have a little extra into the 6th interval that I'm going to need to use, meaning I'm going to use 5 different rates for a full delta x number of seconds, a full 0.9 seconds, and then that 6th rate I'm going to use for a little bit. So think about whether you want to write it out. Don't need to grab a calculator and figure out what t to the 1.3 power is for various values of t. But thinking about this rate function, we can use function notation or substitute into it just as a write a number instead of t sense. Think about how much accumulation of height there's been due to the 5 complete intervals, and then how much accumulation in height there is due to this last partial interval. We decided it was 0.5 extra seconds. Since these are 0.9 each, this 5th interval ends at 4.5 seconds, and I need to get to 5 seconds. So if you haven't written this out, just write down the computations we'd need, whether function notation or with numbers, one way or another. All right, so for the 5 completed intervals, within each interval, if I want to know what's happened to the height due to the time that's passed, that's asking for what's dy based on knowing the rate, m, and how much time has passed, dx. It's just that we keep changing m's, so we can't just say, oh, it's been 4.5 seconds and multiply by a rate. So there isn't one rate. Over that interval, there'd be 5 rates. So we're going to have to work with them each separately. And so, variety of different ways you could write this, but using function notation, I need the rate from the exact velocity function, or r sub h function, whichever you want to call it, v or r sub h, at 0, multiplied by delta t, or 0.9. And then the rate at the beginning of the second interval, which is at 0.9, times the length of time we use it for, 0.9 seconds, plus the velocity at the beginning of the third interval, times the length of time we use it for, and so on and so on. So each of these is an mdx expression. This bottom line is if I, instead of writing out the function notation, if I were to write in what's the value or the computation for the specific rate of change of the height. But again, each of these is a mdx sort of expression. It's just I've got 5 different m's in those 5 complete intervals. But notice that it's the same sort of thing. MDX, 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 there's 5 of them added together. Now if I needed to add together 37,000 of those, I doubt I'd want to write them out one by one by one. So I'd want to find a shorter way to express that, which is our main goal for today. How do I generalize this or write it so that I can do this in any case without having to write a billion things? But just this second question here, within the current delta t interval, there's a variety of ways you could express this. I'm going to give another option other than what I know I have listed on here. But again, it's the velocity or the rate of change of the height from right here at time 4.5 multiplied by how long we use it for, which we could write as dt, or we could write as 0.5 in numbers. Another way we could write this, and I knew that was going to happen, never be so lucky as to have it stay when I need it. The velocity or the rate of change of the height at time 4.5 times, well, this dt here, all that really is measuring how far our current time is from the left end of the interval. And we just talked about, there's a function we're going to define more formally in a minute, but the amount of time that I use this rate for is however far t is, so this is kind of more generic, from the left end of the interval, so left of t. Now, also this one was a specific value of t equals 5. So instead of writing just 0.5 or dt, if I wanted to think about what we were just talking about in general, the left end of the interval, say, oh, well, this is 5 minus the left of 5. Left of 5 is meaning on the x-axis, what's the beginning of the interval most immediately to the left of 5, our current position. So there's a variety of other ways using concepts we've talked about that you can express this, but this is just a way to express how long am I using this most recent rate for. And I can't use left in any of these earlier expressions because if I'm talking about at t equals 5, left of 5 only has one value. Just like any other function, for any independent value given, there's only one output. So if t is 5, there's only one value of left of t, happens to be 4.5. If t is 3.7, this is 3.6 there. If t is 3.7, left of t is that spot right there, which is 3.6. Left of 3.7 is 3.6. It's just talking about the interval boundary that's immediately to the left of whatever x value or independent variable value you're at. So in general, we can call it left of x, and we can define that based on, well, how wide your intervals are and where you started them at. Yeah? All right, so yeah, so left of and then I put a number in here, left of some number, indicates the interval boundary when we split the x-axis up into different intervals, where in each interval we're using one constant rate. So this is talking about the interval boundary that's closest to, but to the left of, whatever number you've chosen. So it kind of rounds back to say what's at the beginning of the interval you're in. So closest to the left, oops, closest, but to the left of whatever number you put in there. So left of 3.7, I'd be looking for what's the interval boundary that's just to the left of 3.7. Oh, 3.7's in this fifth interval. 3.6 is the interval boundary. There's interval boundaries at 0, 0.9, 1.8, 2.7, 3.6. And so if I'm at 3.7, I've just passed that 3.6. So I'm in the interval that starts at 3.6, which is useful to know because the rate used throughout that interval is the rate from the left end of the interval, the rate at 3.6. So let me clear this off. And let's talk about how I would write this out kind of more generally. So if I want to write out a function for the rate, we did this already with the sand. So oil, that's what it was. Was that sand spill? No, oil spill. So think about, how do I explain this approximate function, the one that's given by these horizontal line segments? There's a long way to write it, and there's a short way to write it. The long way to write it is just say, oh, well, like what we did last time, and I'm prepared. I'm going to use the value of my actual function here, v of t or r sub h of t. So at the left end of the leftmost interval, which is 0, and I'm going to use that if t is between 0 and 0.9, right? 0 to 0.9, including the left end. So if I'm at 0, I'm going to use this rate from 0. If I'm at 0.9, though, I'm going to use the next rate. I'm going to use the rate function at 0.9 as long as t is 0.9 to 1.8, including the 0.9. So that's using this rate for the first interval, using this rate for the second interval, and I could say that over and over and over again. But thinking about that idea of left that we just talked about, there's a way I could write this whole piecewise function. Instead of writing it as a piecewise function, I could write it in one line because, well, just as a sentence, said the rate is always based on using the approximate rate. We're using the exact rate from the left end of the interval that we're in. So this approximate rate is always based on using the exact rate, r sub h or v, at not just t, but at the left end of the interval we're in. Oh, the left end of the interval would be left of t. So for any value of t, whether it's 0.4, 3.62, whatever it is, if I want to know what's the approximate rate that I'm using right now, I say, oh, well, what's the beginning of the interval? Use the exact rate from that point. Use the exact rate from the beginning of the interval. So I could write it this way, or using the notation that was in your book, and therefore also here, I could also say this is v of left of t. So I could write a long piecewise function, but if you agree with me from the last problem that those long piecewise functions are really aggravating, we can find a way to write it shorter. V of left of t, or r sub h of left of t, because that gives me always the exact rate of the interval that I'm currently in. So if I want to describe the current rate at any point in time, I just do r of left of, or r sub f or r sub h, whatever the letter is, of left of t. Left of x, whatever your variables might be for the question. So A of t is a little bit harder to write. It's still, we can write it as piecewise, and we can write it not as piecewise. We can write it in a single line. This is what's going to take the work, and we're going to work through it today. We're going to talk about it for a bit. We're going to think about it some more over the weekend, and I'm going to ask you a bunch more questions to make sure you understand it. But A of t is the accumulation up through time t. So if you're from the previous page, and to get the accumulation, we had a bunch of things that were all done. We used like 7 different rates, each one times 0.9. Plus, the last one we had the option of writing left of t's rate and times the dt, or times the little extra different amount. Well, I want to be able to describe how much is accumulated at any point in time. So if I'm in the first interval, easy. If I'm in the first interval anywhere between 0 and 0.9 in this case, I say, oh, well, I'm using left of t times however far I am into the interval, dt, or I could do t minus 0 to tell me how far I am into the interval that started at 0. So let me write that out. So in the first interval, and I'm just going to write this up top, just starting left to right, say, oh, well, I'm using the rate, the exact rate, at time 0, and there's multiple ways to write this again, times, well, however far I am into this interval, which would be, well, how far is t past 0? T minus 0, which is just t, but I'm going to write t minus 0 just to emphasize it's how far I am past 0. And this would be the formula I use, which I could also call this left of t, but it's only left of t if t is between 0 and 0.9, right? If I'm in the second interval, I've got 2 different rates to worry about. I can't call them both left of t, but I can call this one left of t in the first interval. All right, so yeah, if I'm in the second interval, I'd have the full first interval's worth of stuff that already happened. We need to do this in 2 different colors. Stuff that already happened. The full first interval, r sub h of 0, times 0.9. That's done. That interval's finished. Plus, then what's happening in the interval that t is actually in. So this is from the previous interval. This is like my y initial. If I'm in the second interval, I have some stuff that already happened, plus what's now happening at our new second rate. But our new second rate, again, I can say, oh, the second rate is the rate that's at the left end of the interval I'm actually in. So I could say r of left of t times however far I am into this second interval, which is, well, how far am I past 0.9? Don't know. T minus 0.9, right? This is my rate for the second interval. If I'm in the second interval, 0.9 to 1.8. And I'm only going to write one more of these because these get really annoying to write, and then we're going to talk about carefully how to piece this together using sum notation. So you can see there's a lot of adding here to do this more succinctly. But if I'm in the third interval, I've got 2 full intervals worth of stuff that already happened. Whatever happened in the first interval is due to the exact rate at 0 times 0.9, just like before. And for the full second interval, I use the rate 0.9 for that 0.9, plus, I'm going to write this on the next line because it's too much stuff to write. If I'm in this third interval, I'm going to use the rate from the left end of the interval I'm currently in, times how far I am into this interval. How far is t past the beginning of the interval, 1.8. So this is the third piece. I've got 2 full intervals plus what's going on in the third interval. So that left description, again, it only has one value at a time. When I say left of t and my t value is 1.8 through 2.7, left of t is 1.8. So this is saying use the rate at 1.8 for, well, however long. Depends on exactly what t is. But if it's in this third interval, it's something between 1.8 and 2.7, so that this difference here comes out somewhere between 0 and 0.9. So I've got mdx plus mdx plus mdx for each one. But you can also think of the stuff that I have in red as being, well, that's the initial value. That's where we started from everything that was already done, plus what's now accumulating in our most current rate. I can describe how to find that rate using this left idea, and how far I am into the interval by doing the current value minus t minus the beginning of the interval. So I could say t minus left of t also, instead of saying 1.8 if I wanted to. There's a variety of ways to express this, but let's talk about this in general. And so that in general, what I'm going to do is I'm going to take out the 0.9s and call them delta x's. Instead of saying things like 0.9 and 1.8 and 2.7, I'm going to describe those in terms of how many delta x's we're at, like 1 delta x or 2 delta x, how many different intervals we've gone past, or which interval we're in. And since we don't actually have to start at 0 like this problem does, there's one more little twist to it that most general form is going to have. But we've talked about most of, if you saw already in the homework that's due. I bumped the homework 8 back, by the way. I don't know why I had it due as early as I did. To be due next week, just like Tuesday, I think it is. But if I can get out of here. Here we go. Let me just talk about the summations quick. So then we'll get back to our sums. The sum of actual stuff, because we're going to be adding together a bunch of things. So just terminology related to sums. There's the part that's inside. It's called the summand, actually. But the formula that you use, we're not going to do, like if you did things with sums, like in an Algebra 2 class, and you had to learn all these formulas for how to add up 100 numbers, that's not what we're doing. Just the notation and how to write a formula that is doing what you want it to do. What this means is to take the formula, the expression 5n plus 6, and substitute in all the whole numbers from 0 through 4. So there's going to be 5 numbers that we substitute in. And for this first question, if I wanted to sub in 0 through 4, I could say, okay, so it'd be 6 plus 11 plus 16 plus 20. And all that means is just to write out, you can just write it out as a sum, or you can actually compute it. But as a little trickery here, it's kind of annoying when you have sums start at something other than 1. If I wanted to express the same thing in a sum using, and this letter down below, n equals 0 on the bottom and then 4 on the top, those are called the indices. The lower limit of the sum is n equals 0, and the upper limit is 4. N is called the index of the sum, meaning it's the idea of it's a variable. We let it take on a bunch of values, but it's just whole number values, 0 through 4 in the top one. In the second question here, I want j to take on the values 1 through something, and then change the expression from the previous question a little bit so that I can substitute in 1 through something and have it come up with the exact same terms as subbing in 0 through 4 did below. So, and the third one I put on your things to look at before we got here today. Just use some function notation thrown in there. So I've got 3 times f of 1 plus 2k, where I let k take on the values 1 through 3, just the whole number values. So first question says this is, oh, it's like 6 plus 11 plus 16 plus 21 plus 26, right? And I don't know what that adds up to. I think I put it on here. Yeah, 80. So in number 2, first of all, what would need to be the upper limit of this sum in order that it has the same number of terms as the one above? 5. Yeah, 0 through 4 would be the same number of whole numbers as 1 through 5. So, or yeah, 1 through 5. So if I put a 5 up here, I want to use the numbers 1 through 5 in a formula like this, but just slightly different, to make it come out exactly the same. So that when I substitute in 1, I end up getting 6. And when I substitute in 2, for j, notice there's no j in here, I need one, I need to get 11. So what goes in the parentheses? J minus 1, right. So I want the first term by taking no 5s, and so forth. So just a little trickery you can use to make sums behave how you want. We're going to do this in about 2 minutes now, so it was about half an hour a little bit ago. But if you can see this expression here, you don't need to distribute that out or anything, but 5 times a number that's 1 less than j, where j goes from 1 to 5, is the same as 5 times a number 0 through 4. Just making these 1 larger and making what happens to them 1 smaller. All right, and this last one is just, make sure you don't just think this is multiplying and there's some number you're putting in place of f. F is still function notation when it's like this. So just if you're going to evaluate this, it would be 3 times 3 squared plus 3 times 5 squared plus 3 times 7 squared by substituting in numbers 1, 2, and 3. Now, in calculus 2, you'll get a lot more chance to play around with making sums that follow certain patterns and alternate in sign and do this and that and the other thing. That's not our purposes. We're just going to write some sums to express what we need for accumulation. Adding up a whole bunch of MDX sort of expressions. We just have to figure out how to write the input to the rate function so it picks out just the rates that we want and uses all of them and multiplies them by the right amount of time, the right amount of dx. So it's not easy. But again, here's our picture. You know how fast the quantity's value is changing and you want to know how much of it you have. So we know our m's, and we're going to break it down to using one constant rate for delta x units at a time and add together each of those m's, each of those rates, times a delta x, except for the last one, last being like, well, it depends on how big x is, how far this last one is out, and yes, it does. That's a computation that we're going to have as a part of our formula. So just looking at this picture, if A is at that spot there, and I'm going to go up through 6.75, which is where this x is in this version of the picture. So this is similar to what we looked at before, but the A is a little farther from the y-axis. If I wanted to express how much I'd accumulated, I need to know the rate for this first interval, the rate for this second interval, the rate for this third interval, and the rate for this fourth interval, which I don't use for the full length of it. So I'd also need to know how much of that fourth interval I'm going to use. So there's no specifics on here, like this is a little past 2 and that looks like about 3 1/3. So it's a little hard to tell exactly where these are, so just thinking about them generally then. If I want to know the accumulation, starting at lowercase a and going through 6.75, I know I have 1, 2, 3 full intervals and one that's a little bit shorter, just based on this picture. So just visually looking at it. But if I want to express what's in here, so 3 isn't a whole lot of things to write out. I need the rate for the first interval, which would be the rate evaluated where? A, right? And then for the second interval, well, it's at this red dot. That's the place where I'd want to evaluate the rate function and use that for a while. And I don't know what the x value is at that red dot, but I know it's one full interval past a. Yeah, so a plus an extra delta x, right? One delta x past a. Or I've gone through one whole interval when I'm starting my second interval. My third interval starts at this red dot. Any thoughts on what would go, what's the x value?
A plus 2 delta x.
Yeah, a plus 2 delta x. So a is the beginning of the first interval, generally speaking. It could be 0, which would make this all a lot easier to write. But it doesn't have to be. So I have a, and then a plus 1 interval width, a plus delta x, a plus 2 delta x, a plus 3 delta x, and so on and so on. And each of those, the full intervals, the first 3 are all multiplied by delta x. The last one, a little bit messier. It's not delta x, it's something between 0 and delta x, whatever delta x is. I can tell that it just visually looking at it It's not all the way through that interval. So in terms of how to write this using a sum, there's three things to add up that all look basically the same. Each one of them has a rate function times a delta x. The delta x part's exactly the same every time. The rate function name is exactly the same every time. It's just the input to the rate function, meaning where do I evaluate the rate function, that is different every time, but it's not randomly different. It's nice and organizedly different. It starts at a, then a plus delta x, then a plus 2 delta x. So yeah, so thinking about what I've got here, for interval number 1, I'm using a. For interval number 2, I'm using the point a plus delta x, so this is the x value at the start of the second interval. For interval 3, or I'd like to be able to substitute in 3, I want this to be a plus 2 delta x. So it's that j minus 1 trick that we just did. I want to be able to substitute in 1 and have something come out to a, but 2 and have it come out to be a plus delta x. And every time I put in one larger value of the index, I'm getting one more delta x, but it doesn't start at 1 delta x, it starts at 0. So yeah, the j minus 1 trick. In the jth interval, I'm going to have j minus 1 delta x's added onto that a, or I will have gone through j minus 1 intervals to get to the start of the jth interval. So to finish up this sum here, we'll just put that inside. It looks a little messy. Especially something that's confusing is you see two delta x's kind of next to one another. The one that's inside the parentheses for the r is helping us define the independent variable value. So this is like our 0, 0.9, 1.8, 2.7. This is giving me boundary values of those intervals. And this is the delta x that I multiply by. So this is all m, and this is dx in terms of rate times time, whatever you want to think of. So the only term that was different in too many ways to include in the sum is this last one. The rate follows the same nice pattern. It would have been the next term up, but it's not multiplied by delta x or anything that's a multiple of delta x or anything that I could somehow get delta x to turn into that by substituting in the right number. So it's just going to have to be its own separate term added on. So I've got a sum of 3 things plus a 4th thing that's not quite like the other. And so this is the change in the current interval. If you want to think about how do I remember what to put in there, is it j minus 1? Is it j? If you're in the, if you have 3 complete intervals, your current interval starts after you've gone through 3, like this. If I've gone through 17 complete intervals to get to the current interval, the beginning of the current interval is the end of the 17th interval. So to get to the end of the 3rd interval, the start of my current incomplete interval, I add on 3 delta x's, all of the current intervals with. So I need a plus how many complete intervals there are times delta x to make this kind of more general. This is specific to this problem. What if I said, oh, go through x equals 47.2? Well, I don't know how many intervals there are, but if I could figure that out, it'd be a plus however many complete intervals there are times delta x as the input here. Or, as we defined it a moment ago, since that's a little bit of a mess, we'll call that left of x. So a plus 3 delta x, not just the 3 on its own. A plus 3 delta x in this situation has the value of left of x. We'll call this, so this is just 2 things that mean the same, but one is the definition of the other. This left of x, thought it was going to stay for a minute. Left of x, in general, this is how I could find it. Now, all right, so if I want to find left of x, a plus total number of completed intervals times delta x. That's an ugly expression. We can call it left of x because it's nice, but also total number of completed intervals is also kind of vague. It's not a computation. It's a sentence right now. But we can make it a computation, and it's not a very hard one. It's just, it might involve an operation that you hadn't used before, although if you've looked at your recitations assignment that you got in your most recent recitation, or that you were told about in your most recent recitation, you should have heard of it by now. If I wanted to go from x equals 4 to x equals 108 and divide it into intervals that are 0.2 units wide, if I ask you how many intervals that is, it's not something you probably know off the top of your head, but it just involves some basic calculations. So what did I say? If I wanted to go from x equals 2 through 108, let me make it fun, 108.17. If I want to take that interval and split it into sub-intervals, with like delta x equal to, here, I think I said 0.2 before. I'll just use 0.2. Make intervals of 0.2 units wide, and I want to know how many intervals is that? Well, from 2 to 108 point something, I need to split that up into tiny, tiny intervals. What mathematics do we need to do to answer this question? Yeah, subtract and divide. So, yeah, final minus initial over delta x. So 108.17 minus 2 minus 2 all over 0.2, and that probably won't come out to be a whole number. So what does this come out to be? Anyone with a GC or a calculator handy? What is it? 540 something? 530? 530, exactly? No, let's see, 0.2 goes into that. 530.85? All right, so if I say how many complete intervals is that? Do I say 531? 530? 530. Even though that 0.85 makes it closer to 531, it's not a complete interval. That last interval, I'm just almost done with it. So I've got 530 complete intervals and 85% of another interval. So what I really want is to do this computation, final minus initial, divide by delta x, and then round it down, because if there's any fractional parts left over, that's not a complete interval. The function for round it down is called the floor function, and notation-wise it looks like this. So if I write 108.17 minus 2 divided by 0.2 and use this floor function, this comes out to be, and that's built into GC also, it comes out to be 530. And so what that tells me is there's 530 whole number is the whole number part of that division problem, or 530 complete intervals in the context of this problem here. So that floor function rounds numbers down that are in between whole numbers, or integers, I should say. Rounds them down. So the total number of completed intervals, we're going to have we could have a plus something like this times delta x. It's all still kind of a mess. But if I want to explain this quickly, I can say left of x. But the definition of left of x involves this floor function and taking our final, whatever that might be, the current value of x. Sorry. Taking the current value of x minus the initial value of x, dividing by the width of the interval, and rounding that number down to a whole number. So this part inside the parentheses here, total number of completed intervals, could mathematically be explained by that x minus a over delta x, and then rounded down, that floor function. There is a ceiling function also, by the way. We don't use it for anything, but it rounds everything that's between whole numbers up, and it's just the reverse top half of brackets. interesting fact that's not useful for class, but just in case you're curious, it does exist. So a plus big mess delta x is the same as left of x. So left of x can be defined in terms of general operations that everybody knows. Left of x isn't a built-in function in GC or anything else, but it's a quick way to describe what we mean. And anybody taking a calculus class, that once you see that, oh yeah, it's that. We want to describe the left end of an interval. We could do the right end of an interval also, it's just not what we want to do. So that would be the ceiling function. So in any case then, let me clear this off. This left of x is where those little red dots were. As x increases, it only has one value at a time. It's the red dot in this diagram, most recently to the left of the current value of x. So if I wanted to, the last one is about how do I find the value by 6.75? If I wanted to find this for any value of x, whether it's anything to the right of a, even to the left of a, and I don't really know how many complete intervals there are, I know that I have to think about what happens due to complete intervals, however many terms there might be. And then there's going to be one stray term from the current interval, because wherever we are, and it could end up that that stray term is 0. We could be just at the boundary of a full interval. But we'll think about just in case. We'll always add this on in general, and it just might turn out to be 0 as the dx value later. But r of left of x, for any x value, there's one current value of x, and that's the rate that we'd use, the rate at that most current left boundary times dx. Just that instead of writing dx, it would be nice to be able to write it in terms of not a second variable. If you look at this right here, we've got j as an index to this, so j is kind of like a variable. It varies from 1 to, well, however many terms it is that I need to add up, which we'll get to in a second. And then we've got r, which is a function. A is a parameter representing where we start accumulation. This is our index that takes on a variety of values. Delta x is a parameter. How wide are our intervals? R is a function, left is a function, x is a variable. Instead of having another variable dx, since dx is just related to x, it's how far x is past the end of the previous interval or how far we are into the current interval, I can explain dx using left of x, just how far x is from left of x, and I can figure out how many complete intervals I have, the other mystery part that's kind of missing here, with that floor function that we just had a moment ago. X minus a over delta x, and then round it down. That gives me how many full intervals I have. Final minus initial divided by that width, that delta x. And just round it down so that's a whole number on top. So altogether, we can write, instead of having a piecewise function for accumulation where every row gets worse and worse and worse and worse, we have just one fairly frightening looking thing. If you just walked into class and saw that the first day, like, oh wow, that looks awful. But if you break it down piece by piece, it's all based on some basic operations like how many intervals fit in an interval, or like how many intervals can I split this into, that sort of thing, and our MDX computations. I've got a rate times a delta x. Here's an MDX. There's a whole bunch of them, in fact, this many of them, that use the same width. We've used full intervals. Plus, I've just got one stray term. It's another rate times dx, MDX sort of expression. By creating this left function, we can write this more succinctly. We don't have to write the term left. It's just if we don't, we have to write that a plus x minus a over delta x floor times delta x expression in both of those places, and it looks awful, more so than it does right now. So we just create the function left to use for our own purposes to indicate, oh yeah, the left end of the current interval. A quick way to say that, but make sure you know where it comes from. So this is our magic middle of the course sort of thing that we figured out. If I know how fast something's changing at any point in time, I can figure out what happens because of that rate at any point in time using this. Now, this is an estimate. As we said, it's based on pretending we have constant rates for delta x units at a time along the independent axis. But notice that this doesn't say how big delta x is. So although like in some of the things where we were trying to draw it out, we use it as like 0.3 or 0.9 or something. It could be 0.000000001, in which case it'd probably be a pretty darn good estimate. And we could even have, if you're patient enough in GC, you could have GC calculate this sum for you. You could have it graph y equals a of x. If you define all the pieces, you'd have to define the rate function. You could define an approximate rate function as r of x equals left of r of the exact function at left of x. You could define your delta x to have a specific value, pick an a to have a specific value, and then you can change delta x to make it smaller, make it bigger, and see what happens. See what happens if you change the value of a, where you start the accumulation. But if you define all of the pieces of this, the exact rate function, the approximate rate function, and left particularly, GC knows how sums work. It knows what the floor function is. Delta x, you'd have to make a parameter. You could use a different symbol if you want, and define its size, as well as a, you'd have to define its size. But this has all of our pieces in it that put together what we've been trying to figure out how to express in general. For a specific problem with a specific rate function and a given delta x, it's a challenging problem, but it's not too bad. It's just a bunch of multiplications and adding up and evaluating functions. If I want to explain how that process works in general, it takes a bit more work, a little bit of concentration to figure out what all the pieces mean. But this is piece by piece. It's about dy equals mdx for the most part. And as x changes, thinking about the process that we were dealing with, we have complete intervals where I have a delta x, a parameter that defines how long I've used a rate for. And within the current interval, this dx is still varying. It's something between 0 and delta x for any value of x that I were to pick. But you can also see there's like this y final equals y initial plus mdx, because I'm trying to find how much total accumulation. Why am I adding these all together? There's no addition in this. This is just multiplication. Well, if I want to get the final, I need to know what's already happened plus what's going on right now, or the initial value plus changes away from that, from using new rates. And for any value of x, I consider stuff that happened in full intervals, I can think of that as done. That's already done. I used all these rates for a while. I know exactly how long I used them for, but that's in the past. Right now, I'm in this one interval. X is still changing. And so I'm going to append this on as an extra term, something that's still varying and still generating accumulation at this point. But by the time this dx gets to be the size of delta x, it's going to be a lump of finished stuff, get tossed away, and I'm done with the rate that I used with it. Pick a new rate and continue on from there. So it's our two main goals for this first half of the class. First, a little bit less than half. Or to look at constant rates and seeing what happens because of them. Now, our test goes up through this material on Tuesday. We're going to take a look at some of this again. I'm going to have actually over the weekend for you, I have something that's called Weekend Quiz in Canvas. It'll become available to you tomorrow. But what it is, it's just like 3 questions about not using like an unknown generic number of rates, but what if I just have like 3 different rates that I have, and doing some computations like we were doing with rocket basketball, like what's the height by times 6.5 or whatever. Just doing some questions like that and answering questions about expressions and which one expresses, finding the accumulation if I know I'm already in the second interval, things like that. also have a MathAS, like an online homework assignment, where the beginning of it is just using those 1 or 2 different rates, and the second half of it, you'll see this whole summation with all the details written in. This is the details taken out, just overall structure of it. You'll see that, and it'll ask you to identify what the different parts are telling you. There's one other thing I'm going to ask you to do over the weekend that isn't really homework to finish or quiz to do, but just stuff to think about. In this just says, in both this page and the previous page, this just says function R. So function R was our approximate rate function. And the textbook mentions this also. But if I were to, I know this is going to run away on me again. If I were to put in R sub f, or whatever the main function name, meaning using the exact rate function, it actually doesn't make any difference because we've carefully chosen all along to only put in input values, x values, that are at the ends of the intervals. So if I'm only evaluating my approximate rate function at the interval boundaries, then that's exactly the same as the exact rate function is at those places, because that's where I pull those approximate rates from. So in reality, it doesn't really matter if I have R or R sub f, or whatever the letter is, the subscript is, the exact or the approximate rate function in these 2 spots, because at the spots we're evaluating them, at those independent values like a plus delta x, a plus 2 delta x, those are the spots where the 2 match up. It's just that the reason it's written without the f there is because how we're thinking of this is we're not letting it change. There aren't variables inside these at any point. It's just an expression with parameters like a plus a certain number of delta x's, or in the case of this one, left of x, which only has 1 value for a while at a time. So I'm using a constant rate for a while, and so that's why that just plain R was used there to indicate, think about using constant rates for a delta x interval at a time, and we're still doing it even if we write just R sub f, as long as I have something like a plus delta x, some sort of interval boundary point inside, those are the same. All right, so that said, just looking at the pieces of this again, I'm taking a sum where I let j, which is going to show up inside the summand here in this expression after the sigma, vary from 1 up through x minus a over delta x. Remember, x minus a over delta x, and then rounded down, floored. Tells me how many complete intervals I have. So 1 through all of the complete intervals. And this inside part here, a plus j minus 1 delta x, is where I'm evaluating my rate function. So I'm evaluating it at a, and then a plus delta x, a plus 2 delta x, a plus 3 delta x, and so on and so on and so on. Letting this go through all of the complete intervals. Each of those rate evaluations, each of those rate values gets multiplied by delta x, the width of a full interval. So I've got my m delta x for all these complete intervals, all however many of them there are. And then in my current interval, the interval that x is currently in, I can call my rate r of left of x or r sub f of left of x, the rate at the beginning of the current interval, times how far we are into that interval. And so this can take on a variety of values as x increases. For a while, this will increase in chunks at a time. Once I've passed another full interval, I'll add on a whole new completed interval worth of accumulation. But that chunk at a time comes from this part finishing up. So I believe, and I don't know if I can find it quickly, there's a cool animation in the book that explains this whole increasing a bit at a time. Let's see. There we go. Now, if I can find it, it's in this section, but this is a long section. This is section 5.2. Your test covers essentially chapters 3, 4, and 5 up through 5.2. There's a list of topics. Now, let's see. Computing the number of intervals, looking for an animation. that I know is in here. I think this is the one I want. All right, so the completed accumulation, so just the sum part of this, it appears in chunks based on a rate function. Let's see, I think this gets, did you take out part of it? Oh, there we go. No, that's not the animation I was looking for. There's one where it combines the both of them. This is just the current. Here we go. Sorry. All right, so we have our completed intervals, generating accumulation. This is what we saw before. So as x increases, we have accumulation, and then, well, negative rates would cause deaccumulation for a little while. This is just a generic picture, so we don't know what the rates were. But this completed one interval at a time, it adds on and then takes on a value. And it stays the same for a while until we've passed a whole additional interval. So the current interval is changing all the time. As x increases, it changes all the time, but every time I pass the edge of a new interval, I pick a different rate, and then I start over from 0. So dx goes from 0 to delta x, and I keep starting over. But these pieces get appended onto the accumulation that happened before. So if I add the two pieces of them together, what I have is this. I feel like I'm narrating the video, but I don't know what speed it's going at. There we go. So let me pause this for a moment, because this goes really fast. So right now, as x is increasing, right now all I've got is just, I'm in the first interval. All that I've got is the current interval. So I'm starting from 0 and building upward. Now, I passed the end of this first interval. My current interval stuff is starting over from 0, and my completed interval is holding steady for a while, and it's going to stay there until I hit the end of my next full interval, at which point I'll get to add on what happened from the second interval to it. So my completed accumulation, if I'm in the first interval, is nothing. All I've got is current interval. And then in the second interval, I've got a new current interval accumulation that happens. Once I've gotten to the end of that second interval, that extra gets suddenly added to the value of the sum. And then over and over again. So we add or subtract if we've got negative rates at the end of each of the pieces here. But this is sort of a mess of accumulation. What really happens is we have the current and the completed all put together, so that these horizontal lines are just representative of, there we go. The horizontal segments are the completed just holding constant while we're waiting for it to get some new completed stuff to add into it. So what we get overall then, this blue, as you see, if I append the current to the end of the completed instead of starting over from 0 all the time, this kind of jagged blue shape is what we end up with as, oh, that's the total of the completed and the current added together. The red horizontal lines you see sticking out of this all willy-nilly, those are like just the completed on its own. So it's a little bit messy to see all at once, but if you can imagine taking this value here and adding on this much extra, by the time I get to this interval endpoint, that's when I do the adding on. I just stay up here. Oop, and I just started it over. But this section is very interesting. It's just a little bit confusing to know what's going on in each of the graphs. So what we're going to do on Tuesday is kind of a wrap-up of some of this. And we're going to take a look at some animations of what happens if I use this technique. What does this accumulation graph look like? And then what would happen if I made delta x smaller? Because if I have GC, I can make it smaller and see what happens without having to redo anything. All right, that's it for today, though. I will see you next time.